Most students think limits are about plugging in a number, but sometimes that gives you nonsense. Let me show you the real trick behind limits. What is an indeterminate form? An expression is indeterminate when direct substitution gives an expression that does not tell you the limit. These forms require algebraic manipulation or special techniques to evaluate. For instance, 0 over 0 is the most common form requiring factoring or simplification, or infinity over infinity, 0 times infinity, infinity minus infinity are all examples of indeterminate form. Today, we'll focus on 0 over 0 and limits at infinity. Here's our first example. We want to find the limit as x approaches 1 of the function x to the 5th power minus 1 over x minus 1. Clearly, if we substitute x equals 1 into a function, we'll have 0 over 0. We can solve algebraically by factoring and simplifying, but in this case, we will build a table of value to see the behavior of the function as it approaches 1. So first, as the function approaches 1 from the left, we'll look at values slightly less than 1, but values that get closer and closer to 1. For instance, if we start when x equals 0.9, if we substitute x equals 0.9 into a function, we'll see that our function will be equal to 4.095. If we get a little bit closer to 1 at x equals 0.99, our function will be equal to 4.901. And we can find these values by simply plugging the values into the calculator. If we get even closer to 1 at x equals 0.999, the function will be equal to 4.990. So from the left, we went from 4.095 to 4.901 to 4.990. So we can see that these values are approaching 5. If we do the same thing from the right, for values slightly greater than 1 but really close to 1, we can start when x equals 1.1. When x equals 1.1, the value of the function is 6.105. If we get closer to 1 from the right, at x equals 1.01, the function will be equal to 5.101. And even closer to 1 at x equals 1.001, the function will be equal to 5.010. So from the right, we went from 6.105 to 5.101 to 5.010. So once again, these values are approaching 5. The values get closer and closer to 5 from both sides. So our final answer, the limit as x approaches 1 of the function x to the 5th power minus 1 over x minus 1 is equal to 5. Why 0 over 0 is a problem? The indeterminate form 0 over 0 doesn't tell us what we need to know about the limit. It leaves critical questions unanswered. Does the limit exist? Is there a hole at that point? Is there a vertical asymptote? Does it blow up to plus or negative infinity? So that's why we must algebraically simplify first, or in our case, we build a table of value in order to find the limit. Now let's discuss special limits at infinity. Today's main example is the function f of x equals 4x plus 1 over x minus 1. We will find 5 different limits for this function. The limit as x approaches negative infinity, the limit as x approaches 1 from the left, 1 from the right, the two-sided limit at x equals 1, and the limit as x approaches positive infinity. First, let's identify the main features of the function. Remember, our function is f of x equals 4x plus 1 over x minus 1. In order to find the vertical asymptote, we will set the denominator to be equal to 0. If x minus 1 equals 0, in order to solve for x, we will add a 1 from both sides. Therefore, x is equal to 1. So there is a vertical asymptote at x equals 1. For the horizontal asymptote, we will compare the degrees of the numerator and denominator. The numerator, 4x plus 1, is a function of degree 1. And the denominator, x minus 1, is also a function of degree 1. So when the degrees match, y will be equal to the leading coefficient of the numerator, in our case 4, over the leading coefficient of the denominator, which is 1. 4 divided by 1 is 4. Therefore, there is a horizontal asymptote at y equals 4. So we will use these facts in order to evaluate the limits. First, let's evaluate the limits as x goes to plus or negative infinity. As x approaches negative infinity, what we will do in order to solve, we will divide both top and bottom by x. And if we perform the same operation to the numerator and the denominator, our function is still equivalent. So if we divide 4x by x, that will be equal to 4. Plus 1 divided by x is 1 over x. Similarly, for the denominator, x divided by x is 1, minus 1 divided by x is 1 over x. So as x goes to negative infinity, 1 over x will approach 0, because if you divide 1 by a very large negative number, let's say you do 1 divided by negative 999 million, for instance, you will see that that will approach a very small number, which is essentially 0. So our limit will be 4 plus 0 over 1 minus 0, which is equal to 4. As x approaches positive infinity, we will use the same method, divide both numerator and denominator by x, and our function will become 4 plus 1 over x over 1 minus 1 over x. And similarly, as x approaches positive infinity, if we divide 1 by a very large number, that will approach 0. So once again, 4 plus 0 over 1 minus 0 equals 4. Both limits equal 4. Confirming a horizontal asymptote at y equals 4. So we can see from the graph, as x approaches or goes towards negative infinity, the function approaches y equals 4. And similarly, as x approaches positive infinity, or as x gets larger and larger, there is a horizontal asymptote at y equals 4. Now, the one-sided limits at x equals 1. First, we will look at the limit from the left. So as x approaches 1 from the left, remember our denominator is x minus 1. So as x approaches 1 from the left, let's say we plug in x equals 0.9999 minus 1, that will be a very small negative number. Our numerator near x equals 1 or at x equals 1 will be 4 times 1 plus 1, which is 5. So our numerator is positive and our denominator will be a tiny negative number. So if we divide a positive by a very small negative number, that will approach negative infinity. So the limit as x approaches 1 from the left of our function f of x is negative infinity. Now, when x approaches 1 from the right, our denominator x minus 1 will be a small positive number. So let's say you plug in 1.0001 for x. That will be a very small positive number when you subtract 1 from it. Our numerator at x equals 1 is still 5, so that's still positive. So if we divide a positive number by a tiny positive number, this will approach positive infinity in this case. So the limit as x approaches 1 from the right of the function f of x is positive infinity. In order to find the limit, the two-sided limit at x equals 1, the left hand and the right hand limit must be equal. In our case, the left hand limit was negative infinity and the right hand limit was positive infinity. So since the left hand limit is not equal to the right hand limit, the two-sided limit does not exist. So the limit as x approaches 1 of the function f of x does not exist. Let's recap. Here's a complete overview of all the limits we evaluated for f of x equals 4x plus 1 over x minus 1. The limit as x approaches negative infinity is 4. We can see here on the graph as x goes towards negative infinity, the function approaches 4. The limit as x approaches 1 from the left is negative infinity, and you can see here on the graph. As x approaches 1 from the right, the function goes towards positive infinity. And therefore, since the behavior is not the same from the left of negative 1 and from the right of negative 1, the limit as x goes to 1 does not exist. And finally, the limit as x goes towards positive infinity is 4 as well. We can see the horizontal asymptote at y equals 4. Now you know how to handle indeterminate forms and limits at infinity. Thanks for watching. Like, subscribe, and don't forget, math success starts when you stay on the fast track.